So in this exam tile question, we're told that the circuit below shows a battery of electromotive force 16 volts and internal resistance 1.2 ohms. So in this one, they've actually told us the internal resistance. We know everything about our battery. We know its potential difference, the EMF of the cell, and we also know its internal resistance. And we're told it's connected to a 3 ohm resistor in parallel with an unknown resistor R. So in this case, we don't know the resistor outside of our circuit, or one of the resistors outside of our circuit. And actually going through this question, we're going to work out what it is. So we're told the battery supplies a current of 5.4 amps. So this is the setup. This is our cell, as we had in our previous exam style question. We have this 16 volt EMF, and we have this internal resistance of 1.2 ohms, this current flowing in our circuit of 5.4 amps, though clearly we'll have less current flowing in here, and that will sum together to make 5.4 amps. We're told this resistor has 3 ohms, and this resistor is unknown. So they'd like us to calculate the potential difference across the internal resistance. Now this is very simple, we've done this plenty of times. We know that potential difference is just given by the current through the component, the potential difference across the component is given by the current through the component times by the resistance of the component, V equals IR. In this case we know the current is 5.4 amps, and we know the internal resistance is 1.2 ohms. So the potential difference is going to be 5.4 times 1.2. And if you put that into a calculator, you find it's 6.48. which is going to be 6.5 volts, two significant figures, and that's our answer. So for the next part of the question, they'd like us to calculate the potential difference across the 3 ohm resistor. So how do we do that? Well, here's where we use the fact that the potential difference across components in parallel is the same. So we know that the potential difference across these components, which are called V, that has to be the same as the potential difference, that potential difference across this 3 ohm resistor is the same as the potential difference across this resistor here, which is equal to the total potential difference across these components in parallel. If we were to just imagine that they were one component, we'd know that the potential difference across them would be V, and that's equal to the individual potential differences across each of these components. So we know what that potential difference is, but now we can use our conservation of energy and know that we have to sum our potential differences up. So we know that 16 volts, the EMF, the potential rise, has to be equal to the sum of the potential drops, which will be the drop over this one. So we've got a rise here, a drop over this, and a drop over these. So we know that this potential difference has to sum with the one we just calculated to give us our total potential difference, our total cell EMF. So we can just write that out. So we know that our cell EMF is equal to our potential difference across our internal resistor plus the PD across the 3 ohm resistor, or remember that's really just saying that it's equal to the terminal PD, that's this bit, that's the terminal PD, plus the wasted PD, or the wasted PD across the internal resistance. And we know the wasted PD now, we know that that's going to be 6.5 volts, because we've got this, and that's actually quite large, but it's because we've got this relatively large internal resistance and this big cell EMF, and we've got this large, drawing this large current, that is to say. So we know that now it's just going to be our cell EMF is...
Hey guys, to continue watching this video and unlock hundreds of other super concise and exam board specific A-level physics videos, just click the Snap Revise smiley face. Join me today, and together let's make A-level physics a walk in the park.